there is going to be some sort of a resistance here. So they calculated there should be a resistance between them. So T, this is, let's say this is T1, T1 minus T infinity, doesn't matter. So T1 minus T2 is equal to, I'm sorry, the Q, the heat transfer is T1 minus T2 divided by the resistance HA, 1 over HA, and L over K. This is the circumferential, and this is a cross sectional. Okay. Now the problem with this one, okay. So let me tell you that phase of doing it. See, this assumes the same heat is going through all cross sections. That is not true. This is all the heat is coming here. So it's basically K cross section dt dx at x is equal to 0 is the Q. Okay, but in this cross section here, this is not Q. It's not Q because it's already escapes here. So one way to do, okay, so this, if I know the temperature distribution by taking this the gradient at x is equal to 0, I can get the Q. That's one way. Another way is, let's say in each cross section here, this heat is being lost. Okay, so HP dx is the H multiplied area multiplied by T minus T infinity, but T is changing. So obviously 0 to L. So HP dx T minus T infinity, that also gives you the Q. So there are two ways of doing it. So the way this is not correct. Okay, so that's because this assumes the same heat goes through arch cross section. That's not true. Now, there could be a way, approximately, because H was given as 15, something like that. Okay, so I can say what is the average temperature between these two. So you say it's, okay, 150 degree average. So H multiplied by pi dl 150 minus 35. I don't know how much you get out of this. So this has been approximate Q. That's also not bad. And a couple of them taken a formula from the book, but they only, if you look at the formula that they've written down, looks like the units are not correct. They have not used the heat transfer coefficient at all. So they just used the temperature distribution and got it. So I don't know how they got the right answer. So we'll find out. By the way, that I think Krishna is going to check with you Wednesday, your night, like 7 p.m. I'm going to have a quiz. So the quiz will cover all the materials we have so far covered in these 3 quizzes. So maybe all the conduction that we have done, including the one that I'm going to talk about today. So understood here. So how do we do this? So we know the temperature distribution are T minus T infinity, which is theta. We defined it. It's going to be A e to the power of mx plus B e mx, which we know because the calculation was K, the cross-sectional area, d square T over dx square minus H P T minus T infinity plus 0. That's what we got. So when you decide T is T minus is theta, so this becomes theta. This became theta. If I define M to be square root of HP over Ka. So this is the solution. Okay, let's apply the boundary condition. At x is equal to 0, theta is theta naught. Let's just define is A plus B. So A plus B is 165. All right. Now, theta at the end of the n, x is equal to L, is A plus B. So this is like A EML plus B E minus ML is 65. So using this simultaneous equation, so you can solve for A and B. I don't know how much I got. So the answer is, a lot of people have guessed it, like 68 watts or something like that. But the important thing is the method has to be right. Unless the method is right, I don't know how I can give the full credit to that. So anyway, just pay attention to the fundamentals. And I can also, the cosine, the theta was cosine HM minus L, let's see, M minus X. No, it cannot be M minus H. Cosine M L minus X. Sorry. Yeah, this is 1 hour length. So it has to be, so this is cosine ML. So that is a theta. So this assumes at x is equal to L, d theta over dx is 0. You can clearly see that. So, yeah, sin h L minus x at x is equal to L, that has to go to 0. So anyway, this will be satisfied with this solution. So anyway, so this is one of the class problem that classic problem that I can give in the test or wherever. So anyway, pay attention to the fundamentals and the first two problems. And third problem I repeated because the previous test I gave a similar problem and I saw some issues with the answer paper looking similar. So I don't want to go into forensic science. So I wanted to conduct one more exam. But again, the forensic science tells me there was some cross correlation between the papers. So let me find out during the Viva, see what happens. All right. So let's go back to what we were there last class. Last class. No, that's not the one. Okay. Let's see. Okay. So this is where we were. All right. So basically, what we are doing here. Let's see. 20th. So the problem that we have is we have an infinite body. This is at a temperature, some temperature, initial temperature. Suddenly on one particular end at x is equal to 0, it could be x is equal to L, it doesn't matter. But the important thing is the heat flux is along the x direction. So only one dimensional problem, one dimensional heat transfer, transient of course. Then when suddenly applied some temperature at T is equal to 0, what will be the temperature profile inside at some location X and how will it look like? And we found that I can combine the two variable X and T by a suitable variable, similarity variable they combine the time, and look at this here carefully. The units, this is unitless because alpha, which is the thermal diffusivity, is length square over time. So this becomes 1 over length. So this becomes unitless. That 4 became, because of the experience, if you don't have 4, you'll eventually find out that needs to be added. Now, the most important thing is when x is equal to 0, okay, which is here, looks like it is equal to time t is equal to infinity. In other words, even at a large time, this temperature is the same. So eta is 0 is here. That eta could be 0 by two ways. Either x has to be 0 or time is infinity. Okay, so that's the interesting thing. The other way, if eta has to be infinity, either x is infinity or t is 0. Okay, x is infinity as t is 0. X infinity means large distance. At t is equal to 0, what? There is all initial condition. So at x is equal to infinity, there has to be t. It has to be t infinity. So though that all the boundary conditions are satisfied in picking this variable, and I substitute that in the governing equation, and that is how I dt dx, d squared d over dx, and so on and so forth. I perform, and then I put these differentiation onto the governing equation. I get one single partial differential, ordinary differential equation, second order with respect to eta. Now T is only a, temperature is only a function of this non-dimensional variable. I've combined x and T. So it becomes like this, and I can easily solve for this. So when I solve for, assuming that boundary conditions I have, I find that T minus T naught is the surface temperature at x is equal to 0, divided by Ti is the initial temperature everywhere, all through the large distances from the surface is also Ti. So the ratio of this is non-dimensional quantity is equal to error function eta. And error function has to be defined. This is 1 over 2 pi. Where did I get? I don't have it here. Error function is, did I define it here? Maybe I did not. Yeah, error function is nothing but 2 over square root of pi exponential minus u squared du. The 2 over pi is necessary because if I integrate from 0 to infinity, this has to become 1. Okay, that's the reason. So at x is equal to infinity, what should be the temperature? Should be unity. It should be Ti. That is the reason. Should be unity. It should go to 1. That is the reason a 2 over square root of pi as a normalizing factor comes in here in front of the integral. Okay. Now there are other boundary conditions that we can work with, a little bit more complicated. When there is a heat transfer at x is equal to 0 rather than the temperature. Temperature is initially at T, it's 0, but at time till at x is equal to 0, at time 0, there was, I'm sorry, at all times, from x is equal to 0, at all time will be kept at, there will be heat flux coming in, constant heat flux. If I expose the heat flux, then the temperature distribution is given this a little bit more complicated than the expression we showed. I won't show too much problem. So you can plot these temperature variation in time as a function of x. This is basically the surface temperature. And here I hear that the surface temperature is slowly becoming, everything become Ti. Okay, so this is the first problem where at x is equal to 0, I applied everywhere is Ti condition. At x is equal to 0, I'm applying Ti at all times. At all times, T surface or T naught, whatever we like. In case 2 is there's a heat flux coming in here, so obviously it will not be merging at, the temperature won't be the same at x is equal to 0. It will be different temperature depending upon your the slope, depending upon the slope. And here there is a heat transfer coefficient here. There's a temperature outside, the heat transfer coefficient is provided, and if that is the case, the temperature as time goes by, in time as time increases, the temperature profile will look like that. I'm not going to be doing this because it gets complicated, and we don't want to dwell on too many. But let's just do one example. I told you before why such a problem that we are considering here. So this problem is, let's say it's in a cold country, and typically they found, somewhere the surface of the earth can get like minus 15 degrees for over 2 months. I mean, that's a typical. So the question was asked, how deep should I bury my water pipes that is coming into the house? That's a nice, very practical problem. So I'm going to give a few. So I need to get what is the minimum depth. If I go deeper, it'll still be warmer. Which one must place? Remember, during the summertime, everywhere it's 20 degrees. Everywhere the soil is 20 degrees. because there are 10 months, at least 2-3 months will be warm enough that the whole temperature at least 20 degrees everywhere. Okay, that's the assumption we're going to make. Okay, so basically this is the atmosphere here, and I want to bury the pipe here, and it said the temperature is at all time it's minus 15 degree. What happens at 60 days basically in that much hours? So how long will it get? So let me give you some of the properties of the earth. Typically it is silica, so the density is at 20-50 kilogram per meter cube. The conductivity is like very, very low, 0.52 watt per meter degree Kelvin. And the specific heat is about 1840 joules per kilogram degree Kelvin. And the thermal diffusivity K over rho C is about 0.138, 10 to the power minus 6 meters square per second. So you can check on any handbook. Maybe I've given them some I don't know whether I gave you in my PPT. I don't know. So I'm going to plug in. I'm going to calculate at x is equal to m. Okay, at x is equal to m, whatever xm, I don't know that xm. I'm going to determine that over T. That should be the temperature there. Minus Tt, Ti. So what should be this temperature? It should be 0 degree because that's when it's going to freeze. So 0 minus what is the surface temperature at this point? So minus 15 degrees. I'm going to, this Earth is going to get minus 15 for 60 days. So what happens? And initially it's all 20 degrees everywhere. 20 degrees minus Ts is 15 degrees again. So I compute this, I get 0.43. Okay. That 0.43, I gave you a error function table here. I come around. Maybe I should make it a little bit bigger. Can you see all, or this too small? Is it too small? Yeah, I'll just increase it. Okay, so 0.43. So I look at I want to get to, this is what I calculated. Okay, so I go to 0.43 somewhere around here. I'm sorry. Did I calculate the error function? The error function. Yeah, the error function is 0.43. So I need to calculate the argument. Okay, so the error function is 0.43. So approximately about 0.40. So the argument is 0.4340. So error function for the 0.43. So xm is 0.43 0.4 multiplied by 2 alpha, 2 square root of alpha t. So 0.8 multiplied by alpha is square root of alpha t. Did I take that? Yeah, I'm taking the square root of it. So time is 60 days, 24 hours per day, 3600, whatever. That I put the whole thing in seconds and take the square root of that. So I get 0.68 meters. So I need to keep that at least 0.68 meters, if not deeper. At least that's a minimum depth I should keep. So it's an interesting, very practical problem. And such problem can be given, I'm just going to say this is a sinusoidal, really varying like this, what happens? So that's a little bit more difficult. You need to get the max and minimum and so on. So it will be complicated. Okay, any questions on this? Any question? So you have the error table here, and I think I've uploaded this. I'm naming these files as Height Transfer 2020 0102, and then the number next to it, how many slides are there. So I'm going to put a PDF. It's in the Teams location. You can all. I hope are you able to access it? My files. I just recently uploaded it, maybe last week. Anybody?
Yes, sir. We can.
Okay. All right. So anyway, this is available there. Okay. Okay. Now I think this completes. Usually, if you look at the your heat transfer book like Goldman, you find that some numerical conduction is done or numerical heat transfer. But I think you guys are you guys taking the finite element now or next semester?
Next semester, sir.
Next semester, I see. Okay. So maybe since you guys know, if time permits, I might just formulate 1 or 2 classes just to see some numerical heat transfer. How do you compute it? Because these days with the tools available, a lot of this problem can be done numerically. I mean, as engineers, you need to get the solution for the problem. The idea of doing all this post form or getting the theory in your head is to see whether your answers are correct. How do you check it? So it's important to know the fundamentals and do some back of the envelope calculation, simple calculation to see whether you're reasonable, even if you do it numerically. So that is the basic purpose of doing this analytical heat transfer. But the most important thing is you need to compute some of those difficult problems. Like, for example, if I have a fin, let's say I have a fin. I have a fin which is a cross section. This is a large fin there. Okay, so this is the fin. So that this cross section is changing on you. It can be formulated. So as x goes, your area of cross section is decreasing, and this is then. So how do I solve this problem? So this can be numerically done because you can take as x goes, you can write a formula for this from the middle, and you know exactly how much is the width. So you can calculate that and formulate it as a numerical problem. It can be done theoretically too. The book has this problem. Maybe after a numerical thing, we can do it as some sort of a project. We'll see. Okay. Any questions on that? Just excuse me, just a minute. Okay, so I will, if time permits, if we finish everything, I will see, how much we can do. Maybe 1 or 2. If we have 1 or 2 extra classes, we can do some numerical way. Okay. So the next topic, important topic, I think we are going over to convection heat transfer. I think we touched upon it initially as an introduction. So the whole idea of convection. Okay, so let's say there is I'm going to do a counter problem, and you need to go and I don't know some of the numbers. Okay, let's say only conduction exists. No convection. I don't know anything about the convection. Okay, so let's say I have a classroom. The plinth area is like maybe 5 meters by 5 meters. Some height, maybe 5 is too much, maybe 3 meters. Okay, so that's my class size. So if I look at the transient heat transfer, remember there was a Fourier number. So basically what we got was for T over L square. So if this is like an air. So if I want to get approximate time, then let's say this is the Fourier number is of the order of 1, let's assume. So some say like ln square over alpha for air. I don't know what is alpha K over rho Cp. I don't know. I need to check it. I think I've done it before. I have to check my note, I don't. So if I put the number L square, like 25 meters square, and if I put this alpha here, I find times, in other words, if I introduce some heat here, it's going to take 2 hours before we feel the heat. That is not happening, isn't it? So obviously there must be some other way heat transfer must be circulating. So what exactly even though in the microscopically that heat transfer occurs by conduction. In other words, let's say I have a fluid. So I have shown it here, but it's okay. I'll just show it. There's a plate. There's a hot plate. So there's a temperature Ts, and there is a relatively cold fluid is coming at T infinity. So you find that this is temperature is T infinity here, and it goes like this. All right. So if I know how much is the heat transfer, this is basically the temperature profile. So what is the heat flux? The flux that's transferring from the hot plate to the fluid. Basically K of the fluid, not the solid. Nothing to do with the solid. Multiply by, let's say this is the direction y. dt dy at y is equal to 0. So that slope of the thermal profile gives me the heat transfer. This is minus, of course. Okay, now the interesting thing is so the slope here that decides exactly the temperature profile is given. So minus k tt dy at y is equal to 0 is give you. So the microscopically, look at that. Still the conductivity of fluid is involved. Now the convection, the whole objective of convection is to find out what's HTC. What is HTC? Heat transfer coefficient. So that is from Newton's cooling law, H, some sort of an area involved, multiplied by T minus T infinity. Some sort of a T average or mean T minus T average. So this is equal to minus Kf dt dy. So H is a derived quantity. It's not a fundamental quantity. So this is nothing but the heat transfer coefficient, derived quantity. Okay, so if I know the thermal profile, then knowing the conductivity of the fluid, I can define a heat transfer coefficient, equivalent heat transfer coefficient. That is, it basically made the problem simpler, that's all. So a number of, and typically this is to do this problem, I need to know, I need to get the, solve the fluid problem, the continuity problem, continuity equation, the momentum equation, and the energy equation. So I need to solve them to really get the temperature profile and get this quantity. So it's involved, the process is involved, and only very simple problems have been able to be solved. Have been solved solve analytically. For example, laminar flow. Laminar steady state, fully developed flow. Let me explain all that terms. Okay, so what exactly is laminar? Let's say for a pipe, I'm taking a pipe. So this is a pipe. Flow is there, a round pipe. Okay, so there's a flow coming in. So there is the entrance effect. So it's like this, something like that, and slowly becomes like this. And eventually you will find if it's laminar, it becomes a parabolic shape. So these are all up to this is the entrance effect. So this is a fully developed. And it's independent. So let's say that u is the velocity in x direction. Let's say this is the velocity in x direction. So uv w. So velocity vector, I'm going to say uvw, and we'll only solve this problem in 2D. We will not going to worry about 3D. It's very impossible to solve it. So u as a function of only u of is independent of, so du dx is 0. So u is not changing. Once it's developed, everywhere is the same. It's being driven by some sort of a flow, pressure here somewhere, whatever. Okay, so only very simple problems, Poisson flow, and very if it is turbulent, obviously if it is laminar, you find the continuity equation is du dx plus dv dy is 0. This is the continuity. We'll solve all. We'll prove all this. Okay, so continuity. Now du dx is 0, so dv dy is 0. Now v, which is the y direction, velocity is 0. However, on the boundary at y is equal to 0, v is also 0. That means v is identically 0. So only profile is u is available. So only velocity is u, and we can get the u is going to be some sort of a function of the x squared, x over L squared. Okay, so we'll for laminar flow, and then it will be a function of the viscosity or Reynolds number or whatever. So we'll prove all that, but only the point I'm raising is to get analytical solution for the heat transfer coefficient for a general flow field is not possible. So people have conducted experiments, they have done empirically, found out exactly what the heat transfer coefficient is for various situations, turbulent flow, transition flow, and so on and so forth. And even the entrance flow, what effect, what kind of parameters you need to consider. So everything is empirical, and you will find out that after we do a few classes of doing a closed form theoretical solution and everything, we'll say what is the practical way to solve this problem, because my purpose is to solve the heat transfer problem. I'm not a fluid mechanics guy for this particular solving the heat transfer problem. So I got to take that role of a heat transfer specialist and see a practical side to it. Okay, all right. Let's say go back to the what is convective heat transfer in detail. I'm going to go over this particular slide, and we have already explained that. Okay, so the fundamental equation to solve is Navier-Stokes, and you know that's very highly nonlinear. Even with the CFD and everything, the computer power. Still solving a very arbitrary problem is not easy. All right. So the one difference between a solid and a fluid is that the fluid cannot support a shear force. In other words, if I apply a force in a shear direction, it will get continuously, it will strain. The fluid will not stay in one place. It will continuously, completely translate. All right. So I just did a theoretical explanation for the heat transfer. Let's just do a simple problem here. So there is a flow. The air is flowing at 20 degrees centigrade over a flat plate whose temperature, surface temperature is 100 degrees. So there's a 100-degree hot plate and this air is flowing through. At a certain location, temperature is measured as a function of distance from the surface. So as a function of y, I'm plotting the temperature. I get this temperature profile. Hot here and slowly reaches the mainstream flow temperature. That's what this is. Okay. All right. So what is the so find out the heat transfer coefficient. I'm going to use the K value for the air is 0.028 watt per meter, which we could have used this to calculate the K over rho Cp, but it's okay. I will probably find it next time. Okay. Oops, sorry. So let's plug in the number. dt over dy. So I have plotted this. Okay, that's a plotting of the temperature over the function of y. This is the temperature on the x-axis. Y-axis is given in millimeters. So dt dy. So this is the slope. So I know exactly 20 degrees to 100 degree. That's the x variation divided by the y variation is about 1.2 millimeters. So I get about 66.7 Kelvin per millimeter. That's my slope at y is equal to 0. And I'm applying that 66 per kilometer per Kelvin per millimeter. And then K is W per Mars, so I need to get the right units, 1,000 millimeters per meter. So applying that scale factor, I get the heat transfer coefficient is like 23. So you can clearly see if I have to solve this problem in a pipe or a flat plate, I need to know the temperature profile and I need to know the slope at the surface, right at the surface. If I know that, I can calculate the heat transfer coefficient. Okay, and of course, I need to know the thermal properties, thermal physical properties of the fluid also. Anybody has any question here? Okay. All right. So again, I'm going to touch upon a few other areas. And I'm not going to dwell too much on turbulence, but let's assume a flow is going over a flat plate. We're going to consider very, very low velocity, so it'll be laminar. But let's just, you might have already read it in your fluid mechanics, but just recollect that. So there is a laminar region. Once is what happens is, this is the basically I'm showing this in the pink color is all boundary layer is building up. The boundary layer is building up. Once it reaches the critical boundary layer thickness, it becomes unstable. Right here, any small disturbance due to friction or something like that in the flow, it disturbs the flow. There is basically I don't know, you will read the R. Sommerfeld equation and everything, but if you do take a turbulence, then you will feel some wave turbulence is and the disturbance is in the form of waves is generated at this interface, and that disturbs the flow, and you start basically u is not uniform anymore. U is varying with respect to x, and v is not 0 anymore. There should be a y velocity coming up. It's all chaotic. It's a turbulent. So there is a transition region between laminar and turbulent and becomes fully turbulent again. If boundary layer again, after that it builds up. Further, it is a lot at a smaller rate. But so if I plot the the boundary layer, for the velocity boundary layer, there's one layer here, there's what is called laminar sublayer. You know, whenever it reaches, that's a very, very small length, you know, thickness, and there the slope is different. I mean, you need to get the, if I want to get the heat transfer coefficient, I need to get this slope, real, not this slope. So then there is a boundary layer builds up. That is the velocity profile until it reaches the mainstream, the flow velocity, u infinity. Okay, so if I want to calculate the, just like the heat transfer coefficient, if I want to get the stress that's imparted by the flow because of viscosity at the surface, is again, there's a similar term. The stress is given by mu du dy. Remember, earlier we used mu as conductivity to get the heat transfer. So there is some similarity between the stress, the fluid stress, and heat transfer at the surface, at least. Okay, so the transition here to turbulent occurs when Reynolds number, which is the mainstream velocity multiplied by the ax distance divided by the kinematic viscosity, is greater than 5 × 10⁵ in a plate. In fact, in the tube is like much less, like 4,000. The transition occurs between 2,000 and 4,000. However, on a plate, it can be anywhere even a little bit even greater than 5 × 10⁵. This is a non-dimensional number. Okay, on a pipe, there is an entrance effect occurring, as I mentioned about earlier. That slowly builds up the boundary layer, this each on the surface, until it meets here, fully developed flow. Then for laminar, this is a parabolic shape, and eventually it becomes turbulent. When it becomes turbulent, it becomes very sharp here, locally here. This is the turbulent core, they call it. So, and here is the slope is a little bit less. So anyway, so this is how there's a laminar sublayer here, and this is where a slight increase, and this is a boundary layer thickness. So this is a turbulent. It's not parabolic anymore. It's like 1/7 law, they call it, but we'll study that a little bit later. So this is the same thing. This is a velocity profile. This is the forced convection here. I'm forcing some fluid through a plate. However, if plate is not, there's no air being forced, there's no fan or anything like that. There's a plate, it's a hot plate at some sort of an elevation due to buoyancy, because hot air rises, cold air comes down. So there is a circulation occurring here. There's a velocity profile. It's zero at the y is 0. It builds up, and then again 0 at large distances from the plate. So there is a boundary layer of the temperature boundary layer. So that is a build here. Again, I can calculate the heat transfer due to natural convection. So this is no external forcing function on the fluid. It's just purely by buoyancy, because of the density difference. So the driving force is the buoyancy, which is the density difference of the fluid due to the temperature. Okay, so if I put a hot plate, you can see, and then if I have some sort of a smoke here, I can clearly see the pattern. You know, there will be circulation here. I can observe it with the smoke. I'm sure you probably saw this in the windmill in the aerospace laboratory. I hope, I don't know, you've seen it at all. Some of the velocity profile there. Okay, all right. Now in the time remaining, the governing equation in fluids is a little bit more difficult to do it very generally using the integral formulation. But let me recall how I did the continuity equation, just to recollect. I did that when I showed you in the first few classes about the divergence theorem. That is, it translates any vector quantity taken the integral over a surface can be converted to a volume integral by the divergence of that velocity vector. So here I'm going to consider a control volume. This is not a closed surface, by the way. This is a control volume where the mass can penetrate this boundary. So, but I'm keeping this stationary in space, but I'm observing exactly what is happening inside, and then eventually the rate of change of momentum here will be the force applied on this control volume. That is the reason I'm going to consider this volume. So let's say there is a flow and coming out. So at any surface here, small surface area dA, okay, there is a normal vector. So here, what is the outflow here? The density multiplied by the u, some sort of the u is coming in some direction, okay? U is not necessarily normal. It's coming in some direction at this particular point. There is a normal flow, of course. So the outflow is going to be rho u dot dA. dA has got direction because this is how the normal vector is. So the outflow from the surface. So if I integrate over the whole surface, the rho u dA, u is the vector here, okay? U is not a scalar. So rho u dA over the whole surface is going to give me the volume outflow. So let's say it's control volume, this control volume. So what is the conservation of mass? So what is the rate of change of mass inside this control volume is equal to, if it is increasing, is equal to the mass coming in from the surface inside, which is equal to negative of mass going outside, because the convention is the velocity will be positive outwardly. So I'm going to put a negative there. So the what is the rate of change of mass inside? D over dt, the volume integral of rho dV. Rho dV is the mass rate. So d rho, I can, since v is stationary, I can bring the integral inside. So partial change of dV d rho dt dV is going to be my rate of change of mass inside. What is the rate of flow outside, out of the volume is rho u dA. So if I equate that, d rho dt, this rate of change of momentum inside the volume is equal to negative of the volume going outside over the A means the surface area A, not the volume. So I need to convert this into a volume integral. So the divergence theorem is going to be applied here. So the area integral is converted to, so remember, this becomes a scalar because I've already taken the dot product here. This is a scalar. So similarly, this has to be scalar. So del dot u is 0. You know, this is the divergence. Del dot means I dA dx, you know, the Cartesian, j d over dy, and k d over dz. Okay, that's what this is. So this is, I can bring this negative here and then I bring it to the left hand side. Since the volume of this is arbitrary, the integrand has to be 0. So this is the mass conservation equation. So if I convert that, let's see. Okay, so I need to, let me bring my table here. So I don't have very much time, but let's do it. Okay, so everybody understood. So just applying the principle of conservation of mass, I determine my d rho dt plus the divergence of rho u is a scale. It's not a scalar. Okay, u, or it could be v vector, but I don't want to use v because of the volume here. This is 0. Okay, let's go and then look at exactly what this is. So d rho dt. So del dot, so anything del dot rho u is, I can operate this del on both. Okay, since this is a vector operator, this is a scalar. So I get u dot del rho plus rho del dot u. So this is what I got. So let's just rewrite this one. So del dot rho is u dot del. So that's an operator operating on u plus rho del dot u. Okay, what exactly a fluid is incompressible? That means that the material derivative, I will define it in a minute, of rho is 0. In other words, d rho, I am making a distinction between is 0. This is not d rho dt, okay? Let me explain to why. What is d rho dt? Rho in a flowing fluid not only is a function of t, but is a function of x, y, z, and t. Okay. Now, besides, x also is a function of t implicitly. Y is a function of t. So d rho dt means I'm taking the total derivative of t. So first term will be d rho dt plus d rho over dx dt plus d rho over dy dt plus d rho over dz dt. What is dx dt in a fluid? I'm observing a particular particle, its x coordinates continuously changing. Okay, what is dx dt?
Velocity.
Velocity u. Similarly, dy dt is a component, okay, not the vector. d dt is v, dz dt is z. So this whole expression, what does it? Okay, so I'm going to have to change. That's okay. I will draw another picture. It's not a problem. Okay, so yeah.
You had written dou x by dou t. Is it? It's a full derivative, right?
That's right. Derivative. It's called material derivative. That is what makes the. Oops, what's happening? Sorry.
No, so I mean the u, v, and w terms.
Yeah. So okay, u, v, e, w is my. I'm here in this particular context. I'm converting this as a vector. Okay. I should have put a v, but I didn't want to consider. So u, v, w are the three components of the u vector. Okay. So which is dx dt, dy dt, dz dt. Okay, so because I'm observing a particle is moving in the space, so what do I get? A d rho dt is d rho over dt plus d rho over dx. So u d rho over dx plus v d rho over dy plus w d rho over dz. So this can be in a short form written as d rho dt plus u dot, this is a vector, del of rho. So this is 0. So what did I get? D rho dt was this quantity plus rho del dot u. Again, u is a vector velocity, 0. So this is 0. Incompressible means this is 0. So in incompressible fluid, del dot u is 0, which means in the component thing is du over dx dv over dy is 0 in 2 dimensions. So this is nothing but the continuity equation for incompressible flow. Okay, so incompressible flow, since this one material derivative is 0, so this is a 0. So I plug this into my continuity equation. My continuity equation was this plus u rho plus del dot u. So since this is 0 incompressible, del dot u must be 0. So my continuity equation for incompressible flow becomes du dt over plus dv dy is 0. Okay, so I'm not sure whether I recorded the whole thing today. I don't know. Did I record it? Yeah. Okay, somebody else turned it on. Thank you. Okay, so let's see.